Good afternoon, everybody. Can you hear me? Osama,
Yes, yes, I can hear you.
We can hear you.
Saleh, Abdul Majid, Mansur, Mr. Naif. Can you hear me, Mr. Naif? Mr. Naif, can you hear me? I think it is the first class for you. Can you please respond? Can you switch on your mic and talk? Or you can send message through the chat box. Naif Abdulaziz, can you hear me? I am specifically asking you because you have missed our earlier classes and this is your first class. I hope you know what we have done so far. We have missed a lot, almost 2.5 chapters. Can you please converse in English? I'm really sorry. Can you put it up in English?
I believe he is not hearing.
Yeah, but I think he wants to convey something. He has sent a message in Arabic.
Yeah, he said there is no voice.
Okay. But others are able to hear, isn't it?
Sorry?
Yes, we
Others
can
are
hear
able
you.
to hear. Yeah.
Yeah.
So he must switch on his mic. Maybe he might have switched off. Yes, Mr. Osama, anything you want to ask? Please let us converse in English.
Yeah, I'm
We
just
are sending
answering him.
messages. Yes?
I'm just answering him.
Okay, okay. Okay, while we wait for others also to join, anybody have any questions, please? I think Mr. Hesham has not come. He might not join us. Okay. In that case, only 7 of us, 7 students. Okay. Yeah, one thing
Yeah.
I have been telling you about the groups for your project work. I am reminding you again. Please make sure that you define your groups. Send the names of students in each of the group.
When, doctor?
Maybe by today or tomorrow, at least before next class.
Okay, in the group, huh?
Yeah.
Okay.
Yes, you can put it in the group. No problem. The WhatsApp group. Yes. Okay. Any questions, please?
I have one question from last class.
Yes. Please
regarding
go ahead.
the uh, regarding the EX and VX.
EX stands for the expected value. It is nothing but mu.
Mu or mean, right?
Mean. It is nothing but the mean.
And VX, the variance.
Variance. VX means variance. EX is actually it is called expected value. Expected value of X.
Do you have, doctor, the answer for example number 2?
I don't have. So Mr. Naif says I can't hear. Please switch on your mic. Or log in again. Okay, so EX stands for the expected value or the mean, and VX stands for the variance. These are standard, let us say, notations. Is it clear, Mr. Osama?
Yes.
Okay, what was your other question? Do I have the answer for the
Example number 2.
second? No, I don't think so. Was it this one?
I believe it's slide number 14, I guess.
Slide number 14. Okay. I don't think I have got the answers. Okay. Was there any difficulty in answering that?
No, I just want to make sure my answers are correct.
Okay, anybody who has tried? Is it about this one? Sigma xpx is your probability as a mean. It will be 0 times 0.5 plus 1 times 0.3 plus 2 times 0.2. So it will be something like 0.4 plus 0.3, 0.7. 0.7 will be your mu.
For both
Okay.
EX and EY, right?
No. 0.7 I have just calculated for you. Okay. For EY it will be 0.5 plus 0.2. Yes, for both of them it is 0.7. Right.
Okay.
Sorry
Variance
for
you have to calculate x minus mu whole square, then multiply with the probability and add them. You will get the variance.
Okay.
Clear?
Doctor, do you hear me? Can you hear my voice?
Yes, I can hear you, Mr.
Okay,
Ahmad.
thank you. Because I changed the computer, because the first one I couldn't hear anything or also share my voice. Okay, thank you. Sorry for the disturbance.
Okay, absolutely no problem. You are welcome. You have any questions, any doubts?
No, thank you so much. Thank you.
Okay. How about Mr. Osama? Is it clear now?
Yes, thank you.
Okay.
Assalamu alaikum.
Yes, please.
Salam.
I already
Evening.
fixed the issue. It's clear now.
Okay, that's good. Yes, any more questions from anybody before we continue?
No question for me.
Okay, good. Okay, so in the last class we were going through the probability distributions. We have defined what it is. It is nothing but listing of all the outcomes of the variable together with the probabilities. And then we have seen how to determine the mean and the standard deviation for the discrete random variable. And also we have looked at two specific distributions, special distributions for discrete random variables, which are nothing but the binomial and Poisson distributions. So these two distributions are special in the sense that they have got only two outcomes, which in reality will be coming across. Whether something can happen or something cannot happen. Whether something can be a success or the attempt can be a failure. So we are looking at the chances of occurrences of or the successes or successes out of n trials in case of the binomial distribution. And if we know the probability of happening to be very small, and if you have got large number of observations, that is we are looking at, and sometimes we'll be looking at the density of occurrences, maybe in the given unit time or area or volume, then we can look for the Poisson distribution, where there also we have got only two outcomes, that is happening or not happening. And the mean and the variance of the Poisson distributions, we call it as lambda, where lambda is nothing but NP. So which is same as the mean for the binomial distribution. And the variance for the binomial distribution is NPQ, or NP into 1 minus P. So we have looked at the probabilities of R successes or R happenings for the Poisson distribution to be given to be e to the power of minus lambda, lambda to the power of R by R factorial. In any case, these formulae are theoretical in nature. We can make use of the tables, the binomial tables and the Poisson tables for arriving at the probabilities, and we have seen how to make use of these tables as well. Then proceeding further, we have got another set of variables which we call them as the continuous variables. So whenever we have got a continuous variable, then we will be looking for a distribution which is most commonly used distribution, or which is most important distribution. We call it as the cornerstone distribution for the statistical inference, because we'll be making use of this particular distribution very extensively. It has got extensive applications in statistics, and we can see that almost all distributions, or irrespective of the distribution followed by the variable, we can look for the distributions of the mean as a normal distribution. In fact, even the discrete distributions like binomial and Poisson distributions can be approximated to a normal distribution. So in that sense, normal distribution happens to be a very important distribution which is associated with a continuous variable. Okay. Now, I have given you a brief about what is normal distribution. Do you remember? In our last class, yes, Mr. Abdul Majid.
Yes, I have just a question, if you allow me, Doctor, about the type of distribution that we take in the last class. I go through these slides. I know binomial and Poisson distribution, and when we use it, but normal distribution, I didn't find how or where I should use the normal distribution.
Use it. Okay. In fact, I have not told you. I have not told you about more about the normal distribution. I had just introduced and left it. Okay.
Yeah. Okay.
Yeah, we will learn more about that. Basically, the normal distribution is associated with a continuous variable. What is a continuous variable? Can you give me examples?
Time is a continuous variable.
Yes, time is a continuous variable. All measurements which will come out, the heights, the weight, the thickness, the diameter, the volume, most of the measurements which we do, they are all continuous, which can take any value within the given range. Very clear? So whenever we have got a continuous variable, let us say continuous variable is x, then associated with this variable, we have got the two parameters. What are the parameters? The mean mu and the standard deviation sigma. Very clear?
Yes, it's clear.
So associated with any continuous variable x, we say that x follows a normal distribution with the two parameters. The two parameters are mu and sigma, that is the mean and standard deviation. So when once you specify the mean and standard deviation, then the distribution is completely specified. Are you with me?
Yes, we are with you, Doctor.
Yeah.
Okay. So Okay, instead of writing here, let me come back to a white screen. So let me share the whiteboard. So let us say we have got, for example, a variable, a continuous variable. So let x be a continuous variable. Can you give me an example? Let us say the heights of students, the height of the whatever it is. Okay. So let us say we have got a variable x. For example, let us say the heights of students of the class, or heights of citizens of Saudi Arabia, whatever it is. So let us say it follows a normal distribution, in the sense that we say that the variable x follows. Generally, this is the notation we make use of. It says that it follows a normal distribution. N stands for a normal distribution with mean mu. Mean is the mean and sigma is the population standard deviation. Mu is the population mean and sigma is the population standard deviation. So if you are looking at a particular variable x, then we say that x follows a normal distribution. Generally, it is represented as x in this curve. Let us say n, capital N stands for a normal distribution, mu stands for mean, and sigma stands for the standard deviation, the population standard deviation. So once you know the values of mu and sigma, when they are specified, then the distribution is well specified, well defined. Very clear?
Yes.
So for example, if I say that x is the height, then I say that x follows a normal distribution, let us say with mean, let us say 150 centimeters and standard deviation 10 centimeters. So then we are completely specifying the normal distribution, the distribution of x. Now, what are the properties of normal distribution? Do you remember? What are the properties of normal distribution?
The graph is symmetric.
Yes, the graph is symmetric. Let us say if x is the variable, then it is a bell-shaped curve, a bell-shaped symmetrical curve, symmetrical about the mean. So when we say it is symmetrical, it is unimodal. There is only one mode, but because it is bell-shaped and symmetrical, the mean, median, and mode, they all coincide. Very clear? And it looks like the graph I have put here. Now we have seen that there is a formula for that. Fx, what is formula? Anyway, it doesn't matter how the curve is got. 1 by root 2 pi sigma to the power of minus of x minus mu by sigma whole square. Anyway, so it is a symmetrical bell-shaped curve. It extends from minus infinity to plus infinity. X can take value from minus infinity to plus infinity. It can go on and on. Are you clear?
Yes.
And when we say that it is symmetrical, if we keep a mirror at the middle where we have got the mu, then the first half of the curve is the mirror image of the second half. And what is the total area under the curve?
It's equal to 1.
The total area under the curve is equal to 1. So what is the area above mu?
0.5.
0.5, half. And the area below mu is also 0.5. Are you clear?
Yes.
And what is the other one? It is asymptotic. What is asymptotic? The curve is asymptotic. What is asymptotic? What does it mean by asymptotic? Do you remember? It extends from minus infinity to plus infinity, and as we go away from the mean, yes, Mr. Abdul Majid?
Yes, I think we took 3 type of curves. It's positive and negative curves and neutral.
I think what you mean is not reaching 0.
Yes, you are right. Okay.
Yes, yes.
Ahmed is right. What you are telling is about kurtosis, Abdul Majid.
Yeah,
Three
okay.
types surfaces. So here, when we say asymptotic, it extends from minus infinity, so it goes on and on. So if you take the x-axis, it goes very close to x-axis, but it will never touch the x-axis. It is the case both on positive and negative side. It goes on and on, and it will be going closer and closer and closer to x-axis as we go away from the main, but it never touches. It touches only at infinity. So that is a property, we call it as asymptotic. Okay. So a normal distribution, the variable, it is having a bell-shaped, sometimes we call it as mount-shaped, both mean the same, a bell-shaped curve which is symmetrical about the mean, the total area under the mean, under the curve being 1, and it extends from minus infinity to plus infinity, and the curve is asymptotic. Are you with me? Can you hear Mr. Naif?
Yes, it's clear.
Yes, Doctor, I hear you.
Okay. Yeah, Mr. Naif, before I proceed, for my information, have you done any statistics earlier?
Yes, yes, I have.
Okay, so that's good. So far, have you gone through what we have done?
Actually, I'm searching for the slides on Blackboard, and I couldn't find them yet. So if you lead me to the...
Please open your Blackboard. Open your
Yes.
Blackboard, and all the materials are there, I think, in the course content.
Yes, I've opened
In
the
the
course
course
content,
content,
but there are more than one choice. I don't know which one. I went to the course content. I found lots of files, but some of them they don't open. And I want to follow up with you on the same slide you are teaching, and I couldn't find it.
are you not able to find the PowerPoint slides?
Yes, please.
Yes, the PowerPoint slides are the main things which I have been using them in the class also and here also. So the PowerPoint slides will give you an idea about the entire topics or chapter by chapter, let us say.
Yeah,
Starting
but
with introduction. Okay.
yeah, but the files here are called discussions, not.
Yeah, I will come to that. I will come to that. So the PowerPoint slides are basically the topics which we have been covering, starting from introduction. It starts from what is statistics. Okay. So then we have gone through the various descriptive parts, and then we have gone through the other chapter, which is the probability, and then this is the third chapter, I suppose, where we have got the probability distributions. For each chapter, I have provided the discussion questions. Please go through the chapter, understand that, open the discussion 1, let us say, don't go in for Q&A. Just open the discussion 1, answer them, then open Q&A, where you have got both questions and answers, so that you can cross-check your solutions. Okay. Then we have got another set of files, which are SPSS files. I have told how to make use of SPSS. SPSS is a statistical package for social scientists. Now it is IBM SPSS. It is a software. It is somewhat similar to our keying in data is similar to what we do in our Excel, where we first define our variables and then key in the data. And I have explained how to key in the data, and we have seen how to look at the descriptive statistics using Excel. No, you're using SPSS. So one of the examples of outputs I have given in your chapter 1, where how the descriptive statistics will appear. So in the exam, I will be giving you the output, and I'll be asking questions on them. So to that extent, so it is sufficient for you to know how to operate SPSS. You will not be asked to do it during the exam. So you can go to the lab, and anytime you can access our SPSS software. If you have got the software with you, it is absolutely no problem. You can do that with that. Otherwise, you can make use of the software in the lab. Okay.
Okay, thank you so much.
And I have given you what is the methodology of our evaluation, where we will be having our first midterm on 9th of October next month. The final exam will be on 13th of November. There will be a project for 20 marks. So first, the midterm carries 30 marks, the final exam carries 40 marks, and the project carries 20 marks, and the class participation basically based on your attendance. Anyway, I will start taking your attendance from today, nothing to worry about previous one sessions, okay? So it carries about 10 marks.
Oh, okay. So attendance 10 marks, final exam 40 marks, that's 50. And then the other 50, can you repeat again?
The midterm exam 30.
Yes.
And the project work 20.
Great. How many project work?
Only one project, and it could be a group project where I have given you in your syllabus. Go to your syllabus. There is a file attached in the syllabus in your Blackboard LMS. Okay. So you have to select a small data set and make use of the applications of what you have learned. And you have to submit the project and make a presentation towards the end. It can be a group project. I have requested your colleagues also to formulate the groups and let me know before next week. You can join one of the groups.
Okay, great. Sorry, can you repeat the final exam date, please?
The date for midterm is on 9th of October.
No, final.
The final will be 13th of November.
13th of November. Okay.
Yeah, the exams will be face to face. It will be in our classroom G97.
Oh, okay.
So whenever there is exam, we'll be meeting at 6 p.m.
Great.
Okay.
Okay, thank you so much.
6 p.m. at room number G97.
Okay.
Okay, this is our first online class we are going through. So let us see how we can proceed.
Okay.
And one advantage is this class is being recorded. At any time, you can go back to your virtual classroom where the recordings are available. You can choose any of the class and you can go through the recordings any number of times, anytime, anywhere.
Okay, perfect. Thank you so much. Okay.
Yes. So we were going through. Yeah, any other questions before we proceed?
Clear.
No, doctor. No, doctor. Thank you. Thanks.
Okay. Okay. Welcome. So when we look for a variable, a continuous variable, and if we say that it follows a normal distribution, the parameters of the normal distributions are the population mean and the population standard deviation. When we specify the mean and standard deviation, then our distribution is completely specified. We will be interested in finding out or answering certain questions. Let us say if we have got the heights of the students, which follows a normal distribution with mean 150 and standard deviation 10. Let us say this is the distribution of the heights. We may have a number of questions to be answered. What is the probability that the height of student, let us say x, is greater than some value, let us say 165 centimeters. So we want to know what is the chances that a student selected at random will have the height to be more than 165 centimeters. Or we will be interested to know, let us say, what is the probability that the height of student, that is x, is less than, let us say, some other value. You can give any value, 147 centimeters, okay? Or you may be interested to know what is the probability that x lies between any two given values. Let us say between 139 and do you want any other value? You can give anybody.
Excuse me, doctor.
Yeah.
Are you writing on the screen? Because
Yeah, I am writing on the screen. Maybe when I come out of this box, you will be able to see.
okay.
Okay. So I have put up a few questions. Can you see the questions now?
Yes.
Yes, there is a slight gap, about 10-15 seconds. Okay. So we may be interested to answer certain questions like this. What are the chances that the probability of the height of a student to be more than 165 or less than 147 or lies between 139 and 165, like that, any values? So for example, if I want to know the probability of X to be more than 165, then I have got a distribution where the mean is 150. So I have got mean is equal to 150, isn't it? And where is 165? 165, let us say, is more here. So somewhere here. So I have got the value of 165 here. So I want to know what are the chances that the height of the student is more than 165. In other words, I will be interested in this area. Are you clear?
This is clear.
Yes. It's clear.
So I will be interested in the areas above a point, below a point, or between 2 points. So how to get this? So to get this, I have to go back to the probability density function of the distribution and look for the integration of the function between the values 165 to infinity, which is theoretically impossible to do that. Are you with me?
Yes.
Yes, Doctor.
So in general, if you look for any normal distribution with a given mean and standard deviation, it becomes very difficult for us to look for the areas between any two values or above any given value or below any given value, because the problem is we have got infinite number of normal distributions, isn't it?
Yes.
As mu
But
changes, as sigma changes, we have got a new normal distribution. In fact, if you look at the height, there may be some other class where the mean can be 165 centimeters, standard deviation can be 9 centimeters. Or you may be looking at the weights of students where the mean is 55 kilograms and the standard deviation is 3 kilograms. Or if the mean changes or standard deviation changes or both change, then you have got a new distribution. So we have got infinite number of normal distributions, and finding the areas for each of these distributions, it will be practically impossible. So luckily what we have done, or what we have got, is we have got a new variable which we call it as standard normal variate. Standard normal variable, you can say.
it's have a letter Z, right?
Yes, you are right. So standard normal variable is represented by Z. It is a standard notation. So what is standard in this? Standard in the sense that Z follows again a normal distribution. It follows a normal distribution with mean 0 and standard deviation 1. Are you clear? Mu
Yes,
is
Doctor,
0
yes.
and
Yes.
standard deviation is 1. So if you look for the distribution looks like this. If you look not the Z distribution, take the variable Z. So it will also be a normal distribution, no doubt. But the mean will be at 0. To achieve this Z, what we have to do? There is a formula. It is given by the variable x minus the mean mu divided by the standard deviation sigma. Are you clear?
Yeah, clear.
Yes, Doctor.
Z is given by, Z is another variable. X was our original variable. Our original variable was x. So using x, I am defining another variable z. How do we define z? Take the variable x, from that you subtract mu, the mean, and divide by the standard deviation. So you will get a new variable z, and this z always follows a standard normal distribution. So whatever may be the distribution of x, whatever may be the value of mu, whatever may be the value of sigma, the infinite number of distributions, all these infinite normal distributions can be converted to standard normal distribution. Are you clear? Using a single formula, z, the new variable z is defined as x minus mu by sigma. So using this, we will see that the infinite number of normal distributions can be brought down to only one normal distribution, which is our z distribution. So this z distribution also happens to be normal, so we know that it is symmetrical about the mean. The mean happens to be 0, and the variance or the standard deviation is equal to 1. And we have got the tables for the z distribution or normal distribution, which gives you the area between 0 to any value z, if you consider z or z1, whatever it is. So any value 0 to z, the area between 0 to z is given. Are you clear?
Clear.
So the probability of z to lie between 0 and any value is given in what is called the standard normal distribution table or the z table. So how does the z table look like? So let me share it. It is there in your LMS, the normal table. This is your z table. Can you see this? Standard normal distribution, and this standard normal distribution, it gives the area between 0 and z, the shaded area. Are you with me?
Yes,
Yes,
but
yes.
what is the x and y axis represents? 0.00,
The x-axis
0.01.
represents your z. The y-axis represents your relative frequencies or the probabilities.
Okay.
So it is a symmetrical distribution, and the area between 0 and z is given by this table. Okay.
Okay.
Now, how to read this one? How to use this one? Say, for example, just now we had got the heights of the students to follow a normal distribution, isn't it? X was the variable which follows a normal distribution with mean. What was the mean I looked at? I think some 150 or something, isn't it? Standard deviation 10. Okay. So what was our first question? The first question was to find out the probability of x to be. Do you remember what was the question?
I think above 165.
Okay. Let us say it is greater than 165. Okay. Now, what exactly does it mean? So we are looking at the distribution of x. What is the distribution of x? The distribution of x is a normal distribution. So this is how the distribution looks like. Okay. Let us say this is a normal distribution. The mean happens to be 165. The mean is 150. Okay. The mean is 150. And the given standard deviation, the standard deviation is 10. I want the probability of x to be greater than 165. So always draw a graph and see where 165 comes. 165 is above 150. Are you clear? Just out?
Yes.
Yes.
So 165 is above 150. So here is 165, and mark the area of interest by a shade in the shaded portion. So let us say this is the area I want to know. Are you clear? The probability of x to be more than 165. So above 165, this shaded area I want. Are you clear?
Yes, doctor.
Yes, clear.
Okay, what I do is this is the variable x. Now I look for the variable z. What is the variable z? Z is defined by x minus mu by sigma. Are you clear?
Yes, yes.
So z is given by x minus mu by sigma. So I transform this variable x into a z distribution, into a variable z. So the mean becomes 0. And what happens to 165? So 150 has become 0. Because if you use 150 minus 150 by 10, so it is 0. Clear?
Yes.
So let us say 165. I am looking at the point 165. Let us say this is x1. So
It will be-
corresponding to x1, I have got a point z1. Clear?
Yes.
So what is z1? Z1
It's
is
165.
x1 minus mu by sigma. Clear? So it
Yes.
will be 165 minus,
Minus 150 divided by 10.
right, divided by 10. So 165 minus 150 by 10, how much you will get?
1.5.
1.5.
Okay, so you will get it as 1.5. So Z1 is nothing but 1.5. Are you clear? So the area above 165 is same as the area above Z1, that is above 1.5 in your Z distribution. Are you clear?
Yes. Doctor.
Yes.
So probability of x to be greater than 165 is same as probability of z to be greater than 1.5. Are you with me?
Yes. Yes.
Yes. Then how we use?
Yes. So now how to get this probability of z to be greater than 1.5? Now what does this table give? The table gives you area from 0 to z. 0 to z. How do you read z? The first decimal is on the first column, the second decimal is on the first row. Are you with me? If the value of z is 1.25 or 0.25, then what I do? 0.2 I will look at here and 0.5 I look at here. This is the area. Area from 0 to 0.25.
I didn't understand it, sir.
Say I am looking at an example. I take the z to be 0.25.
Z to be not we have now z is equal to 1 point or z1
Yeah,
is
I
equal
will come to that. I will come to that later. So I'm just
okay.
taking an example. If z happens to be 0.25, then how do you read 0.25? So that is important. So here you are looking at the first decimal is 0.2, the second decimal is 5. Are you clear? We split it
Yes, yes.
into 0.2 and 5. 5 is second decimal. Are you with me?
Yes. Yes. It's clear.
So now
So the area from 0 to 0.25 happens to be 0.0987.
Yes. Yes.
Yeah.
I want just to understand. If I'm looking to Z to be 0.42, I go to 0.4 in the column and 0.2
Yes.
in the row, 0.02 in the row, and find it 0.1628. Yeah, that's it.
You are absolutely right. Is it clear?
Yeah, it's clear.
Okay. Now let us come to our problem. So we are looking at probability of x to be greater than 165 is same as probability of z to be greater than 1.5. So I want the area above 1.5. Is this area available in the table?
we have 1.5.
Yes. It's the second row, fifth column.
1.50.
Yeah.
Okay.
0.
1.5 means 1.50, isn't it?
Yeah.
Yes,
Yeah.
right.
Yeah.
It is 1.5. 1.5. Please remember, not 0.15.
Yes.
Yeah,
If we have
confused.
z1 as if we have z as to be 1.53, for example, we will go
Yes.
to this 0.4370, right?
You are right. You are right.
Okay. Thank you.
Perfectly correct.
Clear.
So now our question is 1.50. Okay. our
Yes.
example. So 1.50 is 0.4332. So what is that 4332? Note that it is from 0 to Z. So this area is 0.4332. Are you clear?
Yes. So 1 minus this area, it will give me my answer.
No, I think not one.
Be careful, be careful, be careful.
Half, I think.
Yes. So area from 0 to 1.5 is 0.4332. And the area from 0 and above, this entire area is 0.5. Are you clear?
Yes.
So I am interested in the area above 1.5. So how do you get it?
Minus 0.5. Yeah.
Yes. So 0.5 minus 0.4332. That is our answer. Are you clear?
It's clear. Yeah.
Are you with me? So always
Yes,
draw a graph. It will be clear.
Okay.
Yes. Thank you, Doctor.
Okay. What was our next question? Probability of X to be? What was our next one?
I forget it.
Do anything. It doesn't matter.
Between, I don't know.
Let's say
we come
between
back.
140 and 160
Okay.
or 170.
Let's
Okay,
let's
140.
take an example, Doctor. Sorry, but let's take an example with decimal numbers. I think because I see
Decimal number. Okay, between 140.5. Okay.
Yeah, good.
140.5 and 162.25.
Okay.
Okay. It's take time
You can take it
to.
in.
Yeah. It's clear now. Yeah.
So we are looking for the area between 140.5 and 162.25. So once again draw the graph. Okay. So look for your variable X. So you are looking at the mean to be 150. Okay. So you are looking at, let us say this is X1 and X2. Are you with me? So we are looking at the area between mean is 150. Okay.
Yes.
So 140 to 140.5, it is below 150. So this is 140.5. Clear?
Yes.
And 162.25 is above 150. So this is your X2. I am interested in this area. Are you clear? Are you with me?
Yes, clear. Yes.
Yes.
Now what you have to do? You transform it. You transform it into Z distribution.
Standard normal distribution. Yes.
Standard normal distribution. So in the standard normal distribution, use the transformation. X is Z is X minus mu by sigma. The mean will be 0. Okay. So what will be the value corresponding to 140.5? Let us say Z1.
It will be X minus the mean 150 divided by
so
the
140.5 minus 150 by 10.
Yes.
10, isn't it? Yes. So 140.5 minus 150 by 10. How much is it?
Minus 0.95.
So minus 0.95. Okay. Minus 0.95. Similarly, what will be my Z2?
It will be 1.225.
Okay, so it will be 1.225. Is it clear to all?
Yes.
162 minus 150 by 10. So 12.25 by 10, so 1.225, you are right. So I'm looking at this area. Very clear?
I think this is easier because I just need to find Z1 and Z2 and add them together, right?
Yes. So
But it is an interval, so we shouldn't do like this because we have to.
probability of okay. Less than 1.225. Okay, so here we have seen that probability of x between 140.5 and 162.25 is same as probability of z to be between minus 0.95 and 1 plus 1.225. Now getting area between 0 to 1.225. 1.225 you can round it off to 1.22 or 1.23. It doesn't matter. Okay. Are you with me?
Yes.
Yes.
Okay. So if I take it as 1.22, so what will be my probability?
It will be just a second.
1.2012 0.3888. Are you clear?
Yes. Yes.
Clear.
So this area is 0.3888, 0 to 1.22. Clear?
Yes.
Now what about this area? Minus 0.95 to 0.
The minus, it will make a difference, or it will be the
It
same?
will, no, it will be the same. So it will be 0.9, 0.3299,
32,
0.3299. Oh, 899. I
1,
didn't say
2, 3, 4,
899.
5. It will be 3289, isn't
Yeah,
it?
yeah. 0.3289. Yeah, this one.
Why is it so? We are making use of the property of symmetry. Note that the area between minus 0.95 to 0 is same as 0 to plus 9.95.
Okay. See.
So you are making use of the property of symmetry. Please remember
Yeah.
that.
Yeah. Okay.
You are not ignoring negative. It is symmetrical. Area from 0 to z is same as area from minus z to 0. Are you clear?
Yes.
So that is the property you use to find out this area. Area from minus 0.95 to 0 is same as area from 0 to plus 0.95. So that's why I am looking at plus 0.95. Are you with me?
Yes, because
Yes.
it's symmetrical.
It is symmetrical.
Okay.
Please don't forget that. So
Okay.
now I know this is the area 0.3289 here and 0.3888 here. So if I want to get the entire area, what I should do?
We add them.
We add them. So you add these two, you will get the required probability. Is it clear?
Yes, doctor, I have a question.
Yes.
Is the mean given, or I have to find it out?
This is given. This distribution is given. X follows a normal distribution with mean 150 and standard deviation 10. This is given. The parameters are specified.
Okay.
So then I am looking for the probability of x to be more than 165 or between any two values. Like that, any probabilities.
Doctor, we didn't
Yes.
use greater than or equal or like this, right? Only greater or less than, right?
Yes, greater. Now note that probability of x to be equal to a given value is always 0 because you are looking at the integral of the continuous function.
Yes.
Integral of x to x is always 0. A to a is always 0.
Yes.
So whether I say less than or equal to, it doesn't matter because x to be equal to 140.5 is always 0.
Yes. I see.
So for a continuous variable, probability of x taking one specified value is always 0.
Yeah.
Are you with me?
Yes. It's clear. Because
So
it will be like a line.
greater,
It will be like a line. Yeah, it will be like a line. So the area of the line
yes.
is 0.
Yes, it is 0. At a specific point, it approaches 0.
Yes.
Okay. Yes. Okay. Can you tell me what is the probability of x to be greater than or equal to 140.5? X to be greater than 140.5.
Is
Any
it
of you?
0.388?
No, no, it's 0.5 minus 0.32899.
Always draw a graph. Always draw a rough graph. What is the area I want to know?
I want to know greater than this 0.329899.
Yes. Let us say 140.5 is here, isn't it? I am
Yes.
interested in this area. Above 140 point this. Are you clear? Are you with me?
Yes, yes.
So 140.5 corresponds to negative 0.95. So I am interested in this entire area. Are you clear?
Yeah, yeah, clear.
So how do you get it?
I think we need to know the area between Z and the median. If we
There
know
is
that
median here.
yes, if we know the area between Z and the median, or between zero, I mean the middle line.
The middle line, and which is this Z means the entire thing,
Yeah,
isn't it?
Yes.
The area above Z. You are looking at
Yeah.
the area above Z, isn't it?
Yes.
Above zero. What
Yeah,
is the
it's
area above
0.5.
0?
0.5.
0.5.
We know it.
You
Yeah,
know
but
that, isn't it?
we need to know the area from the middle line and to Z.
So it's
We add them together and
0.32.
we find our area.
Exactly.
Now, what is a Z corresponding to 140.5?
0.3289
0.32.
plus 0.5.
You see, this is value, isn't it? Minus 0.95. So I'm looking at the area from minus 0.95 to 0 and the area from 0 to infinity. If you add these two, you will get it, isn't it?
Yes.
Yes, that's what I mean.
Yes.
So what is the area from minus 0.95 to 0? We already know that.
Yes, 0.3289 plus
89. So
point-
0.3289 plus 0.5. So 0.8289. That is your answer.
Doctor, I think
What do you think?
we should move to whiteboard because it's not clear here.
It's not clear here. Okay.
Yes.
Okay. Shall we go back to whiteboard?
Yes, yes, doctor. But I didn't understand the last part. You add just half to the to Z value.
Yeah, look at the graph. That's why I always want you to put a graph for your variable x. Okay. I want probability of x to be more than 140.5. So I will just draw a graph. This is the graph I come across.
Yeah, yeah.
Okay.
The graph is clear.
So
Yeah.
graph is clear. This is 140.5. Okay. I want above 140.5. So I transform x to z now. Now I will come here. Okay.
Mm-hmm.
So 140.5 is same as negative 0.95.
Right.
So this is same as probability of z to be more than minus 0.95. Are you clear?
Yeah, clear, clear.
Doctor, I didn't get
So
the
more than
0.5.
0.95 is minus 0.95 to 0 plus 0 to infinity. 0 to infinity is known, 0.5. So I want minus 0.95 to 0. It is same as 0 to plus 0.95, which is given here from the table.
Right.
So I am adding these two values, 0.3289 and 0.5.
Okay.
Are you with me?
Yeah, clear.
Okay, just I wanted one more. Can you tell me what is the probability of x to be greater than 162.25?
It's
This
0.5 minus 0.388.
Yes, probability of x to be greater than 162.
We found it here to be 0.388. Yes, this one. So
Yes, we have found 0.3888 is what?
Is the average
The area between 0 and Z2.
Yes.
0 and Z2. Now I want the area above Z2. How do you get area above Z2?
0.5 minus
0.5
0.388.
Minus,
yes, is it clear to all? 0.5 minus 0.3888.
This is clear. Is the same as the first one.
Yes, yes. Is it clear? Any questions, please? How to use the table? Given any two values or any one value, I can find out the value of x to be between two values or above a given value or below a given value using the same table and using the property of symmetry. Are you with me? Any questions?
Clear.
It's very clear.
We can move now. Thank you.
Yes. Okay. Let's move to the whiteboard. Good. It is still there. Okay. Yes. Any other values you want to find out? Okay. I found more than, less than, between.
No, thank you. Clear. It's clear.
Okay. Now, let me ask another question. Knowing the value of Z, I know how to find the area or the probability. Is it clear?
Yes.
So far what we have done, knowing the value of Z, we looked at the first column and the first row. The first column gives us the first decimal, the first row gives the second decimal, and the body of the table gives us the probability or the area. Okay. Now, yes. I will look at the other way. Given the probability, can I get the value of Z?
Yes, I think we can.
So, given the probability, or in other words, given knowing the area under the curve, let us say this is our 0. This is our value 0, this mean for our Z distribution. So, I want to get two values, let us say, which are equidistant from 0. Let us say minus Z1 and plus Z1. Are you with me?
Yes.
So that the area between these two are known. Let us say this is 90%. This is 90% or 0.9. 90%, which is same as 0.9. Clear? So I want to know the values for Z1. What is Z1 such that the probability between, so in other words, I want to know what is Z1 such that the probability of minus Z1 less than Z less than plus Z1 is 0.9 or let us say 90%. So what are the value? What is the value of Z1?
0.45. It will be first. We know that Z1. What I mean is 0.45 is the value that we're looking in the table to know the value of Z.
Perfectly correct. Can you explain why? Can you make it more elaborate?
Because Z1 and minus Z1 are symmetric, so the total is 0.9.
Okay.
So we divide it by 2 because it's symmetric.
Yes. Did everyone get it? The logic behind it?
Sorry?
Did everyone get this point?
So,
clear to all?
Doctor, you want to know the area between 0 and Z1?
Yes. I want the area between minus Z1 and plus Z1 to be 0.9. Okay.
So since it's symmetrical, divided by 2, it will give us the.
So I know that the table gives me the area from 0 to z. This is what the table gives me. 0 to z, isn't it? This is the type of table I have got.
Yes.
Some tables
Yes,
will
right.
give me from minus infinity to z. Cumulative probabilities, other tables will give. Now the table we have got, it is giving from 0 to z. So I want to know the area from 0 to z. What is the area from 0 to z1? This is the table. This is what the area is given in the table.
Because
Are you with me?
it's symmetrical, we add them. Yeah, we add them before, and they
Yes.
are symmetrical now. So we
So
divide
it
it
will
by
be
2
half of
because
0.9. So it will be half of
Yeah.
0.9. So this will be 0.45. Are you clear?
Yes. But if you have, doctor, if you have like Z2 from minus Z1 to Z2, for example, this.
Then you have to define what is this area. Here it is 45%, 45%. It may be 30%, 70%,
Yeah.
60%. So then you have to define what is the area.
Yeah.
That's all. So here I am defining the area to be half of. Are you
Yeah.
clear?
But
So if the
yeah,
area,
it's clear. But I mean,
yeah.
yeah, in
If
case
the
if not
values are
symmetrical,
different, yeah.
yeah,
Then
yeah,
our
because we
Z1 and
will
Z2
add
will
them.
be
So we
different.
need,
Yes.
yeah.
Then
So we need
the,
to go back to the table and know
yes,
some information from the table or
you are right.
like this, right?
So you are perfectly correct. So what I do is, now I will go back to the table and look for 0.45 as the probability or the area or in the body of the table. Where is 0.45 within the table? Are you with me?
Yes,
Is it clear?
Yes.
So I will go back and I will, okay, let me go back to the table. So look for the normal table and look for where is the area which is 0.45.
It will be approximation, right? It's not.
Yeah, it is almost an approximation. Let us try to find out to the best of ability or what the values are given here. Okay.
It's
So these are,
0.
I look for 0.45 in the body of the table. It increases, goes on from 0 to 0.5. Yeah.
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 Yes, it's
So here I look for,
0.1736.
yes,
Right.
you are right.
Okay.
Go ahead.
Yeah, it's clear. We found that from the decimal, the first decimal is 0.4 or 0.4. Then the second one is 0.05. We find the cross of them is 0.1736. So this will be the value of Z, I think.
It is the value.
Yeah.
What is 0.1700? It is the area from 0 to 0.45, whatever it is, isn't it? 1736 is area from 0 to 0.45.
Yes.
Am I interested in that? I want the area to be equal to 0.45.
Yeah, it will be 1.6, 1.65.
Okay, did you get the difference?
Yeah, because I can see the value 0.45 in 1.6,
Yes.
row
So
1.6.
0.45 is somewhere here, 4495, 4505, in between these two, exactly in between 1.64 and 1.65. Clear?
Okay. Okay. Get it.
So because we
this is
have
the area.
the area.
So you are given this area is 0.45. So I am looking for 0.45 within the table, and I am trying to find out what is the value of Z. Are you with me? Is it clear?
Yes. Yes.
So it can be 1.64 or 1.65. Generally, it is taken 1.645 in between. As a standard value, we take it as 1.645. Okay. So probability of Z lying between minus 1.645 and plus 1.645 is 0.9 or 90%. Is it clear?
Yes, it's clear.
Is it clear to all? Mr. Saud, Ahmad,
Yes, clear.
Osama,
Clear.
Naif. Okay. So the probability of, okay, you go back to our whiteboard. So I have now found out that the probability of the value of Z1 is plus or minus 1.645. So probability of minus 1.645 to be less than Z to be less than plus 1.645 is 0.9. Here. Okay, can you tell me if I change from 90% to 95%, what will be the value of Z1?
Sorry.
Well,
Instead of 0.9, I make it 0.95. Do you have the table with you?
Yeah, but give us just a second.
Yeah, take your time.
The value between it's 95.
It is 95 now.
Okay.
I want it to be 95%, 0.95. Same procedure. Divide 0.95 by 2, so it will be
475.
0.475. Okay, so look for
Yes.
0.475 in the body of the table.
1.96.
1.96.
Around 1.9. Yeah, 1.9. Yeah.
1.96.
96, yeah, 1.96. Yeah, okay, I see.
There.
Yeah,
So
clear.
probability of minus 1.96 to be less than Z, to be less than plus 1.96 is 0.95 or 95%. If I make it as 99%, can you similarly get the values?
Yes. It will be 0.495. So we are looking. It will be 2.575.
Yeah, 2.575 or 2.58. So okay, so we can take it as 2.58. Let us say. So minus 2.58 to be less than Z.
Approximation is
Less than.
acceptable, right, Doctor?
Yeah, approximation is possible here because we have got the limitation of having only 2 decimals. There are more extensive tables like Dodge-Robin tables and other tables where you can go up to any number of decimals. They are almost a big book. It is just an extract what we have got. Okay, so you can approximate to the nearest second decimal. Absolutely nothing to worry. So it will be 99% or 0.99. Very clear?
Yes.
So these are some standard values which maybe in future also will be coming across. So 90% of the observations will lie between minus 1.645 and plus 1.645. Or the probability of a point Z lying between plus or minus 1.96 is 95%. Or probability of Z lying between plus or minus 2.58 is 99%. Very clear? So these numbers, if you want, you can remember that, or if we come across these numbers, you must be able to identify that these numbers are got using our standard normal distribution tables. Are you with me?
Yes.
yes, so.
Is it clear to all? Any questions?
Thank you, Doctor. Thank you.
Okay. Another question. Let me say if I take plus or minus 1, from minus 1 to plus 1, what is the area between minus 1 to plus 1 or minus 1 sigma to plus 1 sigma? Let us say I want to know what is the probability that the height of a student lies between 140 and 160 centimeters. It is mean minus 1 sigma to mean plus 1 sigma, isn't it?
Yes, 90.
Yes.
So what is the area under the curve between minus 1 and plus 1? If I call it as plus 1,
It will be the area from 0 to 1 multiplied by 2.
yes, multiplied by 2. You are right.
Yes.
So this area will be how much?
The value of z is 1, right?
Yes, 1.00.
It's will be 0.3413
Okay.
multiplied by 2.
0.3413 multiplied by 2, so it will be 0.6826, isn't it? So almost 68%, can I say? Okay.
Yes.
Almost 68% of the observations will be between plus or minus 1 sigma from the mean. Are you with me?
Yes.
Yes, Doctor.
If you consider minus 2 to plus 2,
It will be 0.4772 multiplied by 2.
0.4772 multiplied by 2, almost 95.4%. So almost 95%, can I say? So about 95% of the observations are lying between minus 2 to plus 2, plus or minus 2 sigma from the mean. Are you clear?
Yes.
Similarly, if you take from minus 3 to plus 3 sigma, minus 3 to plus 3,
It will be 0.4987 multiplied by 2.
0.4987 multiplied by 2, it will be almost 99.8%. Is it clear? Or 99.7%.
Yes, yes, clear.
So we can say that 99.7% of the observations lie between mean plus or minus 3 times standard deviation. Almost all the observations. So these are the two values within which all your observations will lie. So if you look for the example, let us say the heights of students, 150 minus 3 sigma, 150 plus 3 sigma, means it will be 150 minus 30, that is 120 to 180. So 99.7% of the heights will lie between 120 to 180 centimeters. Almost all observations will be within these two limits. Are you clear?
Yes.
Clear.
Okay. So we have seen how to find the probability knowing the value of z, and also we have seen how to find the value of z given the probability. We are using the same table. Are you clear?
Yeah. Yes.
Okay. Now I'll ask one more question. Let us come to another one. I want to find a value of x, that is the height, such that 5% of the, let us say 3% of the students are above this height. Are you with me?
Yes, Doctor.
Okay.
Yes.
Okay, let me try to clear. Okay. So I have got the variable again. So what is the variable? X follows a normal distribution, isn't it? X. Okay, that equals normal distribution. What was the mean? 150. And standard deviation 10. Okay. So this was the distribution where the mean was 150. for x, okay. I want to have the value of x. What is this value? Such that 3% of the students have got height above this. Let us say 3%.
So we are looking for 47%, right? Because 50%, yeah.
So here, this area from 150 to question mark, or let us say x1, okay? So this will be 47% or 0.47. Is it clear?
Yes.
So look for the value of z for which the area from mean to 0 to that z will be 0.47. Can you give me the value?
0.1808.
0. I am looking
1808.
for the value of z. I am looking for the z distribution. Where x1 is becoming my z1. Okay? It means 0.
Is it 1.89 like this?
Yes, this area is 0.47. 1.89.
8.9.
1.89. 0.4. One thing on 1.88 can be more approximate, better.
Yeah.
Isn't
Yeah,
it?
maybe. Yeah, maybe because 1.8.
0.4699. 0.4699 is 1.88.
Yeah, yes.
1.89 is 0.4706. So we can take it as 1.88. Okay?
1.88 is, yeah, because it's 0.4699.
Yes.
Yeah.
Is it clear to all? Can I say Z1 is 1.88? Osama?
Yes,
Any-
it's now
any
clear. Yes.
doubts? So, okay. So how did we get Z1?
Yep.
Z1 is nothing but, what is the transformation? Z1 is x1 minus mu by sigma, isn't it?
Yes.
And now we know Z1. Z1 is 1.88. So knowing the value of Z1, mu and sigma, can't you find out x1?
Yes.
So can you tell me what is x1?
It will be 18.8 minus plus the 150.
Yeah, 150 plus
18.8.
1.8 times 1.88. Okay, 1.88 times standard deviation 10. Okay.
Yeah, it will be 18.8 plus yeah.
It will be 186.8.
168.8. Is it clear?
Yeah.
So
Yeah.
above 168.8 centimeters, we have got 3% of the students.
Just a question. How we get 1.88 again, please?
0.47. Okay.
Yeah.
Come back to our table. Let me open the table. So remember
نفس اللي قبلها
0.47.
نفس اللي قبلها.
Look for our table, Z table. Look for
We look
the area 0.47.
Okay.
0.47 is close here.
Yeah. Okay.
It is more, so
I
this
see. I
one.
see.
Yeah.
I got it.
So this will be
Yes.
1.8 and 8.
Okay.
Okay.
It's clear. Yeah.
Is it clear? Any questions, please?
So, Doctor, this 1.88 is the Z1, right?
Yeah, that is your Z1.
So we might multiply it by 10 and add it to the one to the
Let
mean.
me come back to our whiteboard. This is the transformation, isn't it? Z1 is x1 minus mu by sigma.
Yes.
So Z1 is 1.88. Clear?
Okay.
I want to find out x1. What is x1? Mu is 150, sigma is 10.
Okay.
So what I will do, I will write down. So what will happen? So Z1, what is Z1? 1.88 is equal to x1 minus mu. What is x1? I don't know. x1 minus mu. Mu is 150 divided by sigma. Sigma is 10. So now I am finding the value of x1. Very clear?
Yes. Clear.
So like this, whether it is 3% or 5% or 10% on the right side or left side, you must be able to do. If it is on the left side, it would have been minus 1.88. That's all. Are you clear?
Doctor, this 3% represent what?
That is the 3%. I want to know the height beyond which 3% of the students are there.
Okay.
3% of the observations are there.
So the
Are you
height
clear?
then the student is more than 168.8, right?
Yes.
This is
Above
the number is 3.
Above 168.8. So this is 168.8. So above 168.8 centimeters,
3%.
we have got 3% of students. Are you clear?
Yes.
Similarly, if I want, let us say below a value, let us say x2, so that below this I have got 3% of students. How do you do that? Exactly similar. Only thing is, instead of plus, it becomes minus, because corresponding value of z2 will be negative. Are you clear?
Yes.
Yes.
So minus 1.8. That's it. Are you with me?
Yes, it's clear.
Okay, so if you are clear about all these things, then this is what is given in your slides, nothing beyond. So we go back to slides. So we are using the same table for answering all these questions. Only one Z table,
Doctor,
standard normal
if you want,
distribution table.
sorry, but
Yes?
if you want Z2, if you want Z2, as it's symmetrical, can we subtract 186.8 from 150? Then it will give us like 18.8. So if we subtract 150 from 18.8, we will get x2.
Yeah, naturally
Can
we
I
will
do?
get x2 by subtracting 150 minus 18.8. That is the answer.
Yeah, okay, thank you.
Okay, you are right. Okay, shall we quickly go through the slides now? Any more questions before I go through the slides?
I know it's clear.
Yes,
for me.
Abdul Majid, okay. So normal distribution is the most important continuous distribution, and many distributions can be approximated to normal distribution. So this is one thing you must be very clear. Because of that, we always look for the normal distribution. In fact, if the value of NP, if you are got a binomial distribution, in a binomial distribution, if NP is greater than or equal to 5, NP is greater than or equal to 5, as well as NQ is greater than or equal to 5, then we can approximate a binomial distribution also to a normal distribution. So even a discrete distribution can be approximated to a continuous distribution, which is normal distribution. Is it clear? That's why we call it as the cornerstone distribution for statistical inference. And NP and NQ to be more than 5, most of the situations it happens. If P and Q are sufficiently large enough, then we will get NP and NQ to be more than equal to greater than equal to 5. Okay, so this is the density function, what we call it, let us not bother much about this. So this is the density function, this is the formula. So where the parameters are mu and sigma. Anyway, not much of importance for us. The two facts will help us to calculate the normal probabilities. The normal distribution is symmetrical. That is one thing which you must always remember. And a normal distribution can be transformed into a specified normal distribution called standard normal distribution. So the formula for that is Z is given by x minus mu by sigma. So look at an example. The amount of time it takes to resolve a claim is normally distributed with a mean of 50 minutes and a standard deviation of 10 minutes. What is the probability that a claim is resolved in a time between 45 and 60 minutes? Can you do that now?
So standard
Nice.
deviation is 10 and the mean is 50, right?
50. Mu is 50 and sigma is 10. So I want the probability of x to lie between 45 and 60.
For the 60,
Exactly similar
it's
to-
1.
Yes. You have to find the corresponding values of z on the normal distribution and use the z table. Are you confident of doing it?
Yes.
Yes, we can do it.
Anybody having any doubt? Very
Yes,
similar to what
clear.
we did. So we make use of the transformation z as x minus mu by sigma. So this is the transformation which you must always remember. And we are interested in the probability of x to lie between 45 and 60. So we transform the variable x into standard normal variate, where the mean for the z distribution is 0 and standard deviation and the variance are equal to 1. So probability of x lying between 45 and 60 is same as probability of z lying between minus 0.5 and 1. So now we make use of the z table or the standard normal distribution table and look for the probabilities. So this is the table we had got. So how do you get it? You look for the area from minus 0.5 to 0 or 0 to plus 0.5. It is both the same because we are making use of the property of symmetry.
Symmetry.
So look for the area from 0 to 0.5 and 0 to 1. So add those two values, you will get the area. So 0 to 0.5, so it will be 0.1915 and 0 to 1, 0.3413. So add these two values, you will get the required probability. Is it clear?
Clear.
So look for the area from minus 0.5 to 0 and 0 to 1. So you will get the area. So 0.1915 plus 0.3413, that is 0.5328. Okay.
Yes.
Another example, the number of errors. Yes, please. Any questions?
No, I just think it's clear.
Okay. The number of errors in each file is normally distributed with a mean of 32.2 on 32.2. Not ounces, the number of errors. Okay. So with a mean of 32.2 and a standard deviation of 0.3. Find the probability that a file will contain more than 32 errors. So you are given the mean 32.2 and standard deviation 0.3. I want the probability of x to be greater than 32. Very clear? So x to be greater than 32. So you will be looking at 32, transform it to z. So it will be 32 minus 32.2 by 0.3. So you will get minus 0.67. So I want probability of z to be greater than minus 0.67, which will be 0.5 plus the area from the table for 0.67. Is it clear? Yes. So it will be negative 0.67.
Yeah, it's clear.
So this is how we find out the areas knowing the value of z. Similarly, you can look for z knowing the area. So given the area A, I am trying to find ZA. In other words, I am looking for the probability of Z to be greater than ZA is equal to A. So I try to find out the value of ZA given the value of A. Are you clear?
Yes.
This is also we have seen how to do that. Determine Z which exceeds, which is okay. Determine Z exceeded by 5% of the population. Determines Z such that 5% of the population is below. So in other words, I am looking at the area above the point is 5% or 0.05 and below the point Z minus Z.05 is 0.05. So in between you have got 0.9. In other words, I was looking at the area between the 2 points is 90% or the area beyond the 2 points is 0.05 each. So the value was 1.645. This we have already seen. Is it clear?
Yes,
Doctor,
Doctor, please.
Yes. Yes, Mr. Osama.
can you go to example 8, please?
Example 8. Back. Yeah.
So the minus 0.68 will give us around 0.24, which is the area.
0.2486. Yes. This area will be 0.2486.
So 1 minus this area will give us the.
Why 1 minus 0.2486. I am looking at the area in two parts. This area and this area. Okay. This
Okay.
area is 0.2486. This is the area between these 2 points. Are you clear?
Clear. So we add 0.5.
To that add 0.5. Area beyond mean is 0.5.
Okay.
So 0.5 plus 0.2486, you will get 0.7486. Are you clear?
Clear, yes.
So that's why you draw a graph always, so that it will be very clear what you have to do, whether you have to add two values or subtract two values, take the difference, or add to 0.5 or subtract from 0.5. What you have to do, it will be clear only when you draw the graph. Are you with me? Will you proceed further?
Yes.
Yes.
Okay. So we have looked at how to get the Z value using the same table given the area. Okay, what are the characteristics? It is a bell-shaped curve. It has the same shape on either side of the vertical line from the mean. It has a single peak, that is unimodal. The mean is located at the center of the distribution. You can add mean, median, and mode are same, equal. The distribution is symmetrical. The two tails of the distribution extend infinitely but never touch the horizontal axis. We call it as asymptotic. So this is how the characteristics of our normal distribution. And we have seen that the area between mu plus or minus 1 sigma is about 68%, between plus or minus 2 sigma is about 95%, and between plus or minus 3 sigma is about 99.7%. So almost all observations lie between plus or minus 3 sigma. This also I have seen, isn't it? So this is graphically you can say mu minus 1 sigma up to mu plus 1 sigma, I have got 68% of the observations approximately, and between mu plus or minus 2 sigma, 95%, mu plus or minus 3 sigma, 99.7%. Are you with me?
Yes.
For various values
Yes.
of k, the area between mu plus or minus k sigma. To this I can add 1.645. It will be 90%. Isn't it?
Yes.
Okay, the normal approximation to binomial, as I told you, if NP and NQ are greater than or equal to 5, then we can approximate a binomial distribution to a normal distribution. So even a discrete distribution like binomial distribution can be approximated to normal distribution when NP and NQ are greater than or equal to 5. Are you with me?
Yes.
Okay. Another example, I think this you will be able to do now anytime. So if X is a random variable with mean 100 and the standard deviation of 10, find various probabilities. So this is the probability of X greater than 128 means you correspondingly find the value of Z, 128 minus 100 by 10, so it will be 2.8. So probability of Z to be greater than 2.8. Very clear? So probability of X to be less than 1.13. Something like this. You can always calculate and find the values of Z and the corresponding areas from the table. I hope I can leave it, isn't it? Anybody not confident?
For me, it's clear.
Okay, good. Similarly, another thing, if Z is a standard normal random variable, find the value of Z for which the area between 0 to Z is 0.33729. Area to the right of Z is 0.7123. Area to the left of Z is 0.1736. I hope all these things you can do using the same table.
We do the same, Doctor. Thank you.
Okay, let's try. Okay, another couple of examples. Suppose the owner of a bakery knows that the daily demand for his whole meal bread is a random variable having the mean 400 loaves and standard deviation is 20. What is the probability that the demand for the bread will exceed 450 loaves? Very similar. You have got the mean as 400, standard deviation is 20. I want probability of X to be greater than
450 minus 400 divided
400 divided by 20. So that will be the value of Z. You are right. The average monthly sales of 5,000 firms are normally distributed with mean and standard deviation of 36,000 real and 10,000 real respectively. Find the number of firms having sales over 40,000. How do you do this? You can get the probability, isn't it? Probability of X to be greater than 40,000, where the mean is 36,000, standard deviation is 10,000. So knowing the probability, I want the number of firms. So out of 5,000, if this is the probability, let us say 0.12, so multiply the number of firms with the probability. 5,000 multiplied by the probability will give the number, expected. Very clear?
Again, please, Doctor.
You can find the probability of the firm having sales more than 40,000. Isn't it?
Yes.
It will be 40,000 minus 36,000 divided by 10,000 is the value of Z. So make use of your table and get your probability. Okay. Let us say the probability is 0.7, for example. Okay. So what will be the number of firms? 0.7 is the probability of sales having more than 40,000. How many firms are there? I have got 500 firms. So 5,000 firms. So 0.7 is the probability. So the number of firms will be 5,000 multiplied by 0.7. You multiply with the probability. That will give you the number, NP. Okay.
Okay.
Yeah, it's clear.
Similarly, the percentage of firms having sales between 38,000 and 41,000. So it wants percentage. Put it in percentages. Probability in terms of percentages multiplied by 100. The number of firms having sales between 30,000 and 40,000. Okay. I hope you will be able to do these things now without any problem.
That's
Any
easy.
questions, please? So this completes our topic on probability distributions.
Dr. RS in the 30, example 13, what does it mean, RS?
Reals.
Okay. As a unit.
Some units. Or yeah, it is real, or if you want, you can make it as dollars.
Okay.
Anything. Okay, it is a unit.
Okay. Thank you.
Unit value. For reals, I have just put S. I want, if you want SARS, you can make it. So the real. Or if you want to change it as dollars, you can change it. It doesn't matter. It is unit of value. Any other questions? Okay, this is about our normal distribution, which is very important distribution, where you must be very clear as to how to make use of the normal distribution table, that is Z table, standard normal table, where we have got only one table for answering all types of situations. So these are the various situations which you will come across. Then we will proceed to the next topic on sampling distributions. Okay. Do you require some short break? Do you need it or no?
Yeah, sure. But what's the next topic?
Sampling distributions.
Sampling
Next
distribution.
topic. Yes, let me try to open the file. It is the sampling distribution. Have you heard of this?
Sorry?
Anyway,
Yes.
we will learn about it. Okay. We will learn about this. Maybe after a short break, let us say it is 5:47, let's say 5:50. So 6 o'clock, 10 minutes, 12, 13 minutes break.
Okay.
Will it be okay?
Okay.
Doctor,
Yes.
I don't know if others are with me. Can we take the break for when it prays, so we don't waste
During the
lots of
prayer
time?
time?
Yes, when like after Adhan we take the break, or for the prayer time we take the break instead of taking it now. If you agree with me, and
Okay, if you want break, then also, now we will reduce this duration now, okay? We will have 2 breaks, no problem.
Okay.
Okay. So please let me know when you want to have prayer break. Then also you can have about 10 minutes there. And now we can have about 7 minutes or 8 minutes till 5:55, okay?
okay.
Okay. Okay, are we back?
Yes.
How about others? Mr. Ahmed, Saleh, Abdul Majid?
Doctor, now
Yes.
the break time is came. So if you allow us 10 minutes more, it will be fine.
Okay, you would like to continue with the prayer and come back? 10 more
Yeah,
minutes?
yeah.
Okay, no problem. Another 10 minutes we will have a break and we will meet at 6:05. Okay?
Okay, 6-5.
Okay, okay.
Okay. Are we back? Ahmed,
Yes, doctor.
Sama, Saud,
Yes.
Saleh, Abdul Majid, Mansur.
Yes, yes.
Okay, let's continue with sampling distributions. Okay, before going into sampling distributions, we have seen what is a normal distribution and how to make use of normal distribution for finding the probabilities and all. And here, note that we have told that x, whatever is x. Say for example, here is the height of citizen, isn't it? So it can be anything. It can be height or weight or income or your sales or whatever it is. So here we have considered height of a person or height of the citizen of Saudi Arabia. Let us say the height of the citizen of Saudi Arabia follows a normal distribution with mu 150 standard deviation 10 centimeters. Now, in reality, do we know the values for mu and sigma? Mr. Saud?
Not
Answer?
not most of the time.
It is not possible, isn't it?
Yes.
It may be very expensive, it may be very prohibitive, because generally the populations will be very large. So getting the values for the population mean or the population standard deviation, it will be very prohibitive. It demands lots of resources which we may not be having with us. Are you with me?
Yes.
Yes.
So what happens is, generally we take samples. We take samples and based on the samples, we look for the sample statistics. Note that these are the parameters. This mu and sigma, which we were talking about earlier, they are all parameters. So the parameters for the population, it is very difficult to get. So to overcome this difficulty, what we do, we take samples. We take samples of size n. Are you clear?
Yes.
Yes.
Samples of size, let us say small n. And then we calculate our mean and the standard deviation. So we calculate x bar from the sample, this is our sample statistic, and s from the sample, that is the sample standard deviation. We make use of these statistics, sample statistics, as estimate for the population parameters, mu and sigma. Are you with me? Are you clear? We try to estimate the parameter mu using x bar, we estimate sigma using s, and we estimate p, the population proportion, using p cap, the sample proportion. Say for example, if I want to know what is the fraction of male in Saudi Arabia. So what I do, I take a sample, let us say I take a sample of, let us say about 1,000 people, and out of 1,000 citizens, I may find 600 are male and 400 are female. So I estimate P cap, that is 600 by 1,000, that is 0.6 as the sample proportion, which I call it as an estimate for the population proportion. Are you with me? Is it clear?
Yes.
Yes. So these are called the point estimates. We call them as point estimate. We are estimating mu using x bar, we are estimating sigma using s, and estimating p over p cap, and we are looking for only one value. That's why we call it as point estimate. We are estimating the parameter using the statistic, and we are giving only one value to that, because we are just saying x bar is value for mu, we call it as a point, a single value. We call it as the point estimate. X bar is the estimator of mu. S is the estimator of sigma. P cap is the estimator of P. Are you clear? So because only one value is associated with the parameter, we call it as point estimate. But note that the point estimate may not be a very good estimate, isn't it? Sir?
Yes, B proportion, is it the same as the probability or something else?
No, proportion. Here, somewhat similar, but you are looking at the proportion of successes out of n trials. If you have got n trials and of them x are successes, then I call the proportion as x by n.
Okay.
Are you with me?
Yes.
It is almost like this. It is a fraction is nothing but your probability, otherwise it is a proportion. Proportion of x happenings.
Okay.
Okay?
Yes, clear.
Okay. Instead of one single point, x bar as a estimate of mu, there is some problem with the single point estimate because your sample may be biased. If I am looking at the heights of citizens, it may so happen that the 1,000 samples which I collect, they may all be having the heights very less, so that the prediction for mu becomes very less. Or on the other hand, the values for x, that is the sample, may have tall people, so that my prediction becomes very large. So there is chances of going wrong. Are you with me? So what we do is, instead of looking for a specific value or instead of going in for a point estimate, what we do, we look for an interval. We look for an interval within which the value of mu lies. We call it as the confidence interval. Anyway, we come to that in our next chapter. So as far as now, we look for the point estimate where mu is, x bar is the estimator for mu, s is the estimate for sigma, and p cap is the estimate for p. Now, we have seen that it is difficult to get the values of mu or sigma or p for the population. So what we do is, we will be looking for a sample, and based on the sample, we will be trying to arrive at certain conclusions. We will be trying to analyze the sample. Are you with me? Okay. Is it
Doctor,
clear? Yes.
what what we are using point estimates for?
The point estimator is an estimator for the population parameter because it is difficult to get the value of mu, the population parameter. If I want the height of citizen of Saudi Arabia, then it is prohibitive. I have to get the observations for all the units of the population where the population could be very large. It calls for lots of resources, lot of time, lot of money, isn't it?
Yes, so we are using sample.
So we'll take a sample and make use of the sample mean as an estimate for the population mean. Are you with me?
Yes.
So we'll try to understand more about these samples now.
Okay.
Okay. So for instance, I am looking at, let me clear. Let me say I am looking at the height of citizen. X is the height of citizen of Saudi Arabia. Of the citizen. So to arrive at the height, what I do is I take samples. I take a sample of size. Let us say sample size is n. I take a number of samples. Let us say sample number 1, sample number. Okay. So I take let us say I take sample number 1. Okay. And I have got a number of observations. I have got n observations, isn't it?
Yes.
Okay, so let me say these are the observations. And I look for the mean. So I have got a number of observations. Say for example, the first sample I take in Riyadh. And I take the observations as, let us say, x11, x12, x13, like that up to x1n. Very clear? I take samples of size n, and for these n people, I look for the n observations for the first sample. Are you with me?
Yes.
Yes, Victor.
I calculate the mean of these n observations. Let me say I will call it as x1 bar. Then I take another sample. Let us say I go to from Riyadh, I go to Jeddah. Again, I take sample of n observations. Sample size is n. So let me say there are about 100. So let me say there are 100 observations I will take from Jeddah also, 100 heights. So x21, x22, x23, like that, x2n. Are you with me?
Yes.
Yes.
Is it clear? And I calculate the mean of these n observations. Let me call it as x2 bar. I go to another place. Let us say Abba. I will collect another n observations. I calculate x3 bar. I go to another sample. I take another sample of n observations from other location. I call it as x4 bar. Are you clear?
Clear.
So like this, I am getting the means for different samples of size n. So I am looking at the mean x bar for each of the sample. Now, what is x? X is the height of citizen. I was earlier looking at the distribution of the observations, x11, x12, like that, the distribution of x. Are you with me?
Yes.
Now what I do is, I will look for the averages, the means, that is x1 bar, x2 bar, x3 bar, x4 bar. I take this as my raw data. This is my raw data. I take x1 bar, x2 bar, x3 bar, x4 bar, like that, and using this as the data, I will be looking for the mean and standard deviation of this. Are you with me?
Yes.
Yes.
So this is the mean of x bar.
So mean of the mean.
Similarly, this is the standard deviation of x bar. Clear? Are you with me?
Yes.
Yes.
So I am not looking at x, I am looking at x bar as the variable, where I am collecting samples of size n, different samples of size n from a population. If for the population x, let us say the mean is mu and standard deviation is sigma. If these are the mean and the finite standard deviation sigma, let us say mu of x to be more specific and sigma of x. Are you clear? I am now collecting the observations for x bar and I am looking at the mean of x bar, that is mu of x bar. Are you with me? And sigma of x bar. The distribution of x bar is called the sampling distribution of the mean. Called the sampling distribution of the mean. Are you with me?
Yes.
Yes.
So now we are trying to look at the distribution of x bar. So that is called the sampling distribution of the mean. So we are considering samples of size n from the population with mean mu and standard deviation sigma. So we are looking at all possible samples of size n from the population and we are looking at the distribution of the averages. So the distribution of the averages is called the sampling distribution of the mean. So the sampling distribution of the mean has got a mean which is called mu of x bar and standard deviation of x bar. Now we have got what is called the central limit theorem. Generally it is abbreviated as CLT, central limit theorem. It is a very famous theorem in statistics. It is a theorem. What do you mean by theorem? It is theoretically proved. So it says that irrespective of the distribution of x, we don't know the distribution of x. Are you clear? Irrespective of distribution of x, don't know the distribution. With me? We don't know the distribution of x. Only thing is, we may know that the mean has to be mu of x and the standard deviation is sigma of x. And we are not aware of what is the distribution of x. Irrespective of the distribution of x, the central limit theorem says that x bar always follows a normal distribution with mean equal to the population mean. Are you clear? With mean equal to population mean, and the standard deviation is population standard deviation divided by root n, where n is your sample size. Are you with me?
Yes.
This is a theorem. This is theoretically proved. Whatever may be the distribution of x, irrespective of the distribution of x, do we know the distribution of this population of the heights of citizens of Saudi Arabia? We don't know. It may be normal, it may not be normal, isn't it? Similarly, if you are looking at the daily sales of your company, is it normal? We don't know. It can be skewed. It can be multimodal. We don't know. So whatever may be the distribution of x, if you take samples of size n, and if the samples are sufficiently large, then the central limit theorem says that x bar follows a normal distribution with mean equal to population mean, and standard deviation is sigma by root n, where sigma is the population standard deviation and n is your sample size. In fact, to be more specific, the central limit theorem says that x bar approaches normal distribution as n increases. For sufficiently large sample sizes, x bar follows a normal distribution. It approaches the normal distribution. That is the actual central limit theorem we have got, wherein it says that as n increases, the distribution of x bar is more closer to the normal distribution. So for larger sample sizes, we can safely assume x bar to follow a normal distribution, irrespective of the distribution followed by x. Are you with me?
Yes.
Is it clear?
Yes. Clear.
So this is the result which we make use of, wherein we assume that for larger sample sizes, as a rule of thumb, if the sample size is greater than or equal to 25 or 30, let us say if it is greater than or equal to 30, then we can safely say that x bar always follows a normal distribution with mean equal to the population mean and standard deviation sigma by root n. By chance, if x follows normal distribution, if x is normal, then all sample sizes, for all sample sizes, x bar is always normal. Even if you take sample of size 2 or 3 or 5, even then x bar will follow a normal distribution, if x is normal distribution. Are you clear? Are you with me?
Yes. Yes.
So this is the result which we will make use of, where the sampling distribution of the mean is always a normal distribution for sufficiently large sample sizes with mean equal to the population mean, that is mu of x bar is equal to mu of x. Is it clear? The mean of the samples is equal to the population mean, And the standard deviation of x bar is standard deviation of x divided by root n. Where n is your sample size. Is it clear?
Yes.
So this sigma by root n, that is a standard deviation of x bar, we call it as the standard error of the mean. There is a name given to that. It is called standard error. Standard error of mean. Are you with me? Sigma by root n. This is called standard error. Is it clear?
Yes.
Okay, now we know that x bar follows a normal distribution with mean mu and standard error sigma by root n. So now we can transform this x bar to z, isn't it? Where z is a standard normal variate. What will be the formula? Earlier, when we were having a normal distribution, if x follows a normal distribution with mean mu and standard deviation sigma, in the last chapter, what did we do? What was our z?
X minus mu.
X minus mu by sigma, isn't it?
Yes.
That is, we took the variable, subtracted from that the mean, and divided by the standard deviation. Are you clear?
Yep.
So what will happen to now x bar follows a normal distribution with mean mu and standard error sigma by root n. So what will be my z?
X bar minus mu over sigma over
Root n. Are you
root
clear?
n. Yes.
So the formula for z becomes x bar minus mu by sigma by root n. This follows a standard normal distribution. Are you with me?
Yes.
This is my z.
Doctor, why we use x bar? Why not x itself? Because we are targeting.
Because x is our variable, we don't know the distribution of x. First thing, isn't it?
Yes.
Do we know the distribution of the population? Do we say, for example, the heights of citizens of Saudi Arabia, or the weights of citizens, or the daily sales of your company, or the whatever it is, the diameter of or the amount of water which is filled in your 1 liter bottles? Do you know that it follows a normal distribution? We don't know.
We don't know, yes.
Isn't it?
Yes.
So that assumption we cannot make. So now what I am trying to do is, I am trying to make use of the distribution of x bar. We know that x bar follows normal distribution irrespective of the distribution of x. Whatever may be the distribution of x, x bar follows normal distribution using my central limit theorem.
Okay, so
Are you clear?
okay.
So I am making use of the result of central limit theorem, which says that for sufficiently large sample sizes, whatever is my x distribution of x, x bar always follows a normal distribution. So that I want to make use of. So I am forgetting about the distribution followed by x. Irrespective of what is the distribution of x, I don't bother about it now. I know that x bar follows a normal distribution if I take samples of 30 or more. Are you clear?
Yes, clear.
So because of that, we'll be interested in looking for this sampling distribution of the mean. So when we look for sampling distribution of the mean, I know that x bar follows a normal distribution with mean equal to mu and standard deviation sigma by root n. So I now make use of the transformation z. So the transformation is the variable minus the mean divided by standard deviation. So x bar minus mu by sigma by root n follows a standard normal distribution. Are you clear?
Yes. Yes.
So z, that is x bar minus mu by sigma by root n, it follows normal 0, 1. So now I make use of the same z table for arriving at the probabilities of x bar lying between any two values. So I will be looking at the average height of citizen between any two values, or above a given value or below a given value. Are you clear? Are you with me?
Yes. So,
Yes.
doctor, we are using the sampling if there is a large.
Yeah, large populations, and when we don't know the distribution of the variable x. So in reality, most of the times we will be looking at the distribution of x bar. Okay.
Okay.
Now, z is given by x bar minus mu by sigma by root n. Good. Now, is sigma known? What about this sigma? Do we know sigma? Population standard deviation? Most of the times it is not known. Clear?
Okay.
Are you with me?
Yes.
If sigma is not known, what we do? If sigma, okay, I will write sigma. If sigma is unknown, we use what? We use S. Sample standard deviation, isn't it?
Oh, yeah.
We use S in place of sigma. So what I do, instead of sigma, I take S. So the formula becomes x bar minus mu by S by root n, and that I no longer call it as Z, I call it as T. Are you with me?
T, okay.
So T is given by x bar minus mu by S by root n. Shall I take it out? Shall I remove this? Shall I clear the blank whiteboard? Saud? Sama, can I clear this?
Yes.
Okay. Okay. So we know that Z is given by x bar minus mu by sigma by root n. Clear?
Clear.
And if sigma is unknown, then we replace sigma by S, and we don't call
Z
it anymore as
by
Z
T.
distribution, we call it as a T distribution. A T distribution where the formula becomes x bar minus mu by S by root n. Are you clear?
Yes.
So we use T distribution when sigma is unknown. Use T distribution and sigma, that is population
Doctor.
standard deviation, is unknown.
Doctor.
Yes, please.
Even S is unknown, right?
This is your sample standard deviation. You have got a sample and you can estimate it, isn't it? You know how to calculate standard deviation for sample?
For example,
Sigma
yeah.
Yes, sigma x minus x bar whole square by n minus 1 under root, isn't it?
Yes.
So we use S for instead of sigma. Use S instead of sigma. Clear? So we call it as a T distribution, or sometimes it is called student's T distribution. Student's T distribution is given by x bar minus mu by s by root n. Student is the name of the person who has discovered this distribution. Now we say that there is no a single T distribution, we have a family of T distributions. Very clear? It is defined by what is called the degrees of freedom. Degrees of freedom. The degrees of freedom is defined as 1 less than sample size, n minus 1, where n is your sample size. Very clear? So we have got a family of T distributions which are very similar to our Z distribution. What happens is, instead of only one Z distribution, if you look for T, then we have got a family of T distributions. The T distribution may look like this, or it may go up like this. The mean is always 0 and the standard deviation is more than 1. As the degrees of freedom increases, the T distribution approaches the Z distribution. If you call this as our Z distribution, let us say the degrees of freedom here may be, let us say it is the df, we can take it as 10. And this is more flatter. This one, we can call it as the df is, let us say 5. As the degrees of freedom increases or as the sample size increases, then the T distribution approaches the Z distribution. Are you with me?
Doctor, what do you mean by degree of freedom?
The degree of freedom is defined as 1 less than your sample size. If your sample size is 10, then degree of freedom is 9. We have got one distribution for each degree of freedom, whereas a Z distribution is an approximation for all degrees of freedoms. For larger degrees of freedom, the T distribution approaches Z distribution. In that sense, for each sample size, we have got a separate distribution. So the T distribution happens to be more accurate than our Z distribution. For each sample size, we have got a separate T distribution. So all the softwares we use, they don't use Z distribution, they use T distribution because they are more accurate. Are you with me? Is it clear?
So for each sample, there is a new T distribution?
Yeah, for each sample size, if your sample sizes changes from 25 to 26, so for 25 sample size, the degrees of freedom will be 24. For 26 sample size, degrees of freedom will be 25. So you have to look for a different table. The values of, let us say, Z or T, it changes. Earlier, we were looking for the T value, Z values, isn't it? If we are looking at 90% within the two values, it was 1.645 minus 1.645. Now, if you have different degrees of freedom, it may not be less or minus 1.645, it can be slightly different, where it will be more because it is flatter. The variance is more than 1. So it may be minus 2.3 or minus 2.145, less or minus that. The mean is 0. The mean is 0, but the variance is more than 1. Are you clear?
Yes.
They are also symmetric. They are also bell-shaped. The mean is 0, but the variance is larger. As the degrees of freedom increases or as the sample size increases, the T distribution approaches the Z distribution. So we have got infinite number of T distributions. Are you clear? That's why we call it as a family of T distributions. Are you with me?
Yes.
Okay. So when sigma is unknown, then we use the T distribution with n-1 degrees of freedom. So for each sample size, we have got one distribution and a corresponding table. Okay. Anyway, we'll come back to more details in our next session, maybe in the confidence intervals. Okay, we'll come back to that. Okay, let us look at our Z. Z is x bar minus mu by sigma by root n, where sigma by root n is called the standard error of the mean. Are you clear? Now,
Standard error.
Standard error, sigma by root n is standard deviation of x bar, isn't it? Standard deviation of x bar is called standard error of mean. Are you clear? Are you with me? So the standard error of mean is nothing but sigma by root n. This is what we have seen, isn't it? X bar follows a normal distribution with mean mu on standard deviation sigma by root n. The standard deviation sigma by root n has got another name which we call it as standard error. Is it clear? Yes or no? If it is clear, I can proceed.
Yes, Doctor, yes.
Okay. Okay. So the standard error of mean is given by sigma by root n. Now, in case the population is small and our sample size is large, if n, capital N is finite and small n is, let us say, greater than 5% of population of capital N.
So it's more than 5%, we will consider it as large.
As large, okay?
Okay.
Say for example, our population is 100 and I take a sample of 30. So it is 30%, isn't it? So it is more than 5%.
Yes.
So what we do is we apply what is called a correction factor. We apply finite population correction factor. Correction factor for standard error. Very clear? So what is the correction factor? The standard error, let us say sigma of x bar. This is the standard error, isn't it? Standard deviation of x bar. This is the standard error. It is given by sigma by root n, the original value as it is, multiplied by the correction factor. What is the correction factor? The correction factor is given by root of n minus n, capital N minus small n, by n minus 1. Is it clear? So
yes.
This particular root of n minus n by n minus 1, we call it as the correction factor, the finite population correction factor.
In capital, we mean the whole population?
Yeah, the population size, which is finite. If we have got finite population and the sample size is larger than 5% of the population, then we apply the correction factor for the standard error of the mean. So the correction factor is given by root n minus n by n minus 1. So the standard error of the mean becomes sigma by root n multiplied by root n minus n by n minus 1. Note that if capital N is very large, then this n minus n by n minus 1 will be 1. It approaches 1. So there is no need for the correction factor. So for infinite populations, we can just take sigma by root n as the standard error. For finite population with large samples, more than 5%, then we can consider the correction factor. Are you with me?
Doctor,
Yes.
how the sample could be more than the population?
Yeah, if we have got a, as I told you, we have got a population, let us say 200 people. or 200 units. So you are taking a sample of, let us say, about 30 of them. So it becomes 15%, isn't it?
Yes.
So in those situations, we will go for the population, finite population correction factor
Okay.
for the standard error. For infinite populations or very large populations, or if the sample is very small, then we don't look for the correction factor.
So, Doctor,
Yes.
if it was less than 5%, we will use the infinite population?
Yeah, if it is less than 5%, just take sigma by root n as your standard error.
Oh, okay.
No need for a correction factor. Are you with me?
Yes.
Okay. So with this background, let us go to our slides. Okay, before I proceed, let me tell you our first midterm is on 9th of October, 3 weeks from now, isn't it?
Yes.
For first midterm, we will have topics up to and including normal distribution. Okay?
So we don't have the sample distribution in the midterm?
Yeah, the sampling distribution we'll have for the final exam. Okay?
Doctor, how about the introduction?
Introduction is there, 3 chapters. Introduction, probability, and probability distributions.
Okay.
Okay.
The 3 chapters and 3 discussions. Okay? So it will be for 30 marks. We will have, let us say, about 20 multiple choice questions for about 90 minutes, 1.5 hours. Okay? On 9th of October.
How many questions?
Starting from 6 p.m. Yes?
How many questions?
20 questions, 30 marks.
Okay.
20 MCQs.
It will be
for 30
MCQs,
marks.
right?
Yeah.
Okay.
20 MCQs for 30 marks. Okay. Chapters 1 to 3.
From
Yes.
chapter 1 to chapter 3?
Yeah. Chapter.
Okay.
It is your introduction, probability, and probability distributions.
Oh, okay.
Both discrete and continuous. Okay. So it will be at 6 p.m., isn't it?
Yes.
So it will be at 6 p.m. at the college, at our room B97. Okay. So please note it.
So, Doctor,
Yeah.
just to make sure, it will be the introduction, random variables, probability, and probability distribution?
Yes.
Okay.
Including binomial, Poisson, and normal distributions. Is it clear?
Yes.
So it will be in the college. Maybe you can bring your laptops if you want, or you can use the computers in the lab. So if you are more comfortable with your laptop, you can bring the laptop. The exam will be in your LMS, in your Blackboard will be answering the questions.
Doctor, we will need to use some calculation using the Excel or
You can use
SPSS.
Excel, you can use calculator. You are free to use anything.
Okay.
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 Only thing is you have got 90 minutes. Duration is 90 minutes.
Okay.
1.5 hours. 6 to 7:30. Okay. So you can bring your calculators, you can use Excel or SPSS if you want, you can use it. So you are free to use any software. You can refer to your tables, your formulae, your material, everything you can use, no problem. But duration is 90 minutes. Very clear?
Yes.
Okay. So now let us go back to our slides on sampling distribution. These things what I have told are there. Okay. As I told you, in real life, calculating parameters of populations is prohibitive because it will be populations are very large and the resources we have got is very limited. We don't have the sufficient resources for carrying out large studies where we can include all the units of the population. So instead of investigating the whole population, what we do, we take a sample. We take a sample and calculate the sample statistics related to the parameter of interest. So we use this sample statistic to arrive at decisions, to make inferences. So we make use of the sample statistic to arrive at the decisions rather than the parameters. So what are the sample statistics? X bar we use instead of mu, we use S instead of sigma, and we use P cap instead of P. So the sampling distribution of the statistic is the tool that tells us how close the statistic is to the parameter. So we'll be trying to look for the different, how we can make use of the statistic, sample statistic instead of the parameter by looking at the distributions of the samples. Okay, so this we already know. A sample statistic is a measure based on the sample, whereas we have got the population parameter is a characteristic based on the population. So related to the population, the characteristic of the population we call it as the parameter, and the characteristic of the sample we call it as the sample statistic. So an estimator of the population parameter is a sample statistic. So and the estimate of the parameter is a particular numerical value, thus we call it as the point estimate. So a point estimate is a single value used as an estimate of the population parameter. So if you use X bar for mu, then it is a single value. Sample mean is a single value. So we call it as a point estimate. So as I have told you, X bar is the point estimate for mu. So we consider X bar as a estimate for mu, and S square is the estimate for sigma square, or if you take the square root, we have got S is the sample standard deviation, which is the estimator for our population standard deviation, that is sigma. And if you take the sample proportion P cap, it is an estimator of the population proportion P. So these are the commonly used estimators for the parameters mu, sigma, and P. So the sampling distribution of X bar is the probability distribution of X bar of all possible values of the random variable X bar. This X bar must be here anyway. So the sampling distribution of X bar is the probability distribution of all possible values of the random variable X bar that may assume when a sample of size n is taken from a specified population. So if you take a number of samples of size n, we calculate x1 bar, x2 bar, x3 bar like that. So we look for the distribution of X bar. So the distribution of X bar is called the sampling distribution of the mean. So the central limit theorem, as I told you, this is the basis for our sampling distributions. When sampling from a population with mean mu and finite standard deviation sigma, the sampling distribution of the sample mean will tend to be normal distribution with mean equal to mu and the standard deviation sigma by root n as the sample size becomes large. Say for example, you can say as a thumb rule, n can be greater than 30. So for large enough values of n, x bar follows a normal distribution with mean mu and variance sigma square by n or standard deviation sigma by root n. So this standard deviation sigma by root n, we call it as standard error of the mean. Very clear? Say for example, if we have got a discrete distribution, if the sample size is 5, the distribution may look like this. If the sample size is 20, it may look like this. For larger values of n, it will be normal. Or if you look at any distribution, let us say if you have got a multimodal distribution like this, a general distribution. If you take samples of size 2, the distribution will be skewed distribution. Whereas if you take samples of size 30, it becomes a normal distribution. Similarly, if you look for a skewed distribution as distribution of x, if you look for the population x, if it is skewed also, then for n is equal to 30, then we have got the distribution of x bar to be normal. Even if it is uniform distribution like this, then for x is n is equal to 30, it will be a normal distribution. If it is a normal distribution, then for even n is equal to 2, it will be a normal distribution, and n is equal to 30, it will be a normal distribution. For all sample sizes, if x is normal, then x bar always will be normal. So the central limit theorem applies to sampling distributions from any population. So any population, whatever may be the distribution of x, it doesn't matter whether it is uniform or skewed or a multimodal distribution, x bar is always a normal distribution. So that is the advantage we have got. That's why we make use of the central limit theorem to look and discuss about the distribution of x bar, not x. Is it clear? So again, the expected value of the sample mean, that is the mu, is given by mu of x, and the variance is sigma square by n, or the standard deviation is sigma by root n. The standard deviation of sample mean is known as the standard error of the mean. So standard error is nothing but the standard deviation of x bar, that is sigma by root n. Are you with me?
Yes.
Yes.
Okay, so let us look at an example of the sampling distributions. Mercury makes a 2.4 liter V6 engine used in speedboats. The company's engineer believes the engine delivers an average horsepower of 220 HP and a standard deviation horsepower of 15 HP. So this is the mean and this is the standard deviation. A potential buyer intends to sample 100 engines. What is the probability that the sample mean will be less than 217 HP? So you are taking a sample of 100 engines. So this is your n. Are you clear? So the mu is given to be 220 HP and standard deviation of the motorboats is 15 HP. So you are taking a sample of size n x bar, that is n, that is 100, and I want to know the probability that sample mean, that is x bar, will be less than 217. Are you clear?
Yes.
Are you with me?
Yes.
So here we are taking samples of size n, that is 100. So we are making use of the central limit theorem, which says that x bar follows a normal distribution with mean mu. So we know that x bar follows a normal distribution with mean mu. What is mu here? Mu is 220, clear? 220 HP, and standard deviation, that is standard error, given by sigma by root n. Sigma happens to be 15 divided by root n, root of n is 100. So the standard deviation is 15 by root 100. Are you clear? So this is the distribution of x bar. So knowing the distribution of x bar, I am looking at probability of x bar to be less than 217. So what is the formula for z? Z is x bar minus mu by sigma by root n. So z is less than, same thing. So you are looking at the distribution of x bar. Its mean equal to 220. So you are looking at the probability of x bar to be less than 217. 217 is somewhere here. I am looking at this area for distribution of x bar. Are you clear?
Yes.
So once again, what I do, I transform this into a z distribution. I transform this into a z distribution where corresponding to 217, I will find the value of z1. So which means 0. So I will look for z1, where z1 happens to be 217 minus 220 by sigma by root n. So it is minus 2. So z1 happens to be minus 2. So I'm looking at the area below minus 2 in the z distribution. Is it clear?
Yes.
So that happens to be 0.0228. So that's how we make use of the application of central limit theorem by looking at the distribution of x bar. I am not interested in the distribution of the horsepower of the motorboats, of the speedboats. I don't know. It is not given also. It only says what is the mean and standard deviation. So I'm taking samples of size n and using the central limit theorem. Any questions, please?
Doctor, what if it was more than 270?
If it was more than 217, what will happen? Can anybody answer? I want the probability to be more than 217, this area. What do you get?
0.5 plus
0.5 plus the value for minus 2 to 0.
0.772, right?
Whatever it is. Yeah, you will get from the table. Yeah?
Okay.
So you can get the value from the table for minus 2 to 0. Or if you know this value, 1 minus this. That's all. Total area is 1. Anyway, if you know this value, 1 minus this. Otherwise, it is 0.5 plus area from 0 to 2. Minus 2 to 0 is same as 0 to 2. Are you clear?
Yes.
So whatever may be the question, you must be able to answer. So here basically we are applying the central limit theorem for the distribution of x bar.
Clear.
Can you proceed? Sama? Ahmad Ali?
Yes.
Okay. Okay, then we have got the student's t distribution when sigma is unknown. When sigma is unknown, what we do? We replace sigma with s. So our
What
formula
is?
becomes x bar minus mu by s by root n, which we call it as a t distribution with n minus 1 degrees of freedom. So note that t distribution is a family of distributions. There are an infinite number of t distributions, and the t distributions approaches the normal distribution, that is z distribution, as the degrees of freedom increases. So t distribution is also very similar to our z distribution. The mean is 0. Only thing is the variance is more than 1. It is more flatter. Are you clear? So that is what is given here. The T is a family of bell-shaped and symmetrical distribution, one for each number of degree of freedom. So the expected value, the mean is 0, and the variance is greater than 1. So it is more flatter, but it approaches 1 as the number of degrees of freedom increases. So as n increases, the t distribution approaches a standard normal distribution. So the t distribution approaches a standard normal as the number of degrees of freedom increases. So when sigma is unknown, we use t distribution. And t distribution happens to be more accurate because we have got one distribution for each sample size. So all the softwares use t distribution and not z distribution. Is it clear?
Yes.
So when we have got finite population and our sample size is more than 5% of the population, we make use of the finite population correction factor. As I told you, we use finite population correction factor, which is given by root of n minus n by n minus 1. So we multiply the standard error by the correction factor. The correction factor happens to be n minus n by n minus 1. When do you use it? Only when capital N is finite and small n is more than 5% of the value of the n, capital N. Same thing again, for finite population, we can make use of the finite population correction factor, and for infinite population, just use sigma by root n. No need for the correction factor. Another example, the amount of soda pop in each bottle is normally distributed with mean 32.2 ounces and a standard deviation of 0.3 ounces. Note that it is given that it is normally distributed. The distribution of X is also given with mean 32.2 and standard deviation 0.3. Find the probability that a carton of 4 bottles will have a mean of more than 32 ounces. So what is N here? What is sample size?
N.
Yes.
4.
4. Okay. So you are given N as 4. So you know the mu is 32.2 ounces. You know the standard deviation sigma is 0.3 ounce. So you are taking sample of 4. Because the X is normally distributed, X bar is also normally distributed. So I want the probability of X bar to be more than 32. So I want probability of X bar to be more than 32. So make use of the normal distribution. So if we have got the variable X bar, so we have the mean to be 32.2. So X bar to be more than 32 is the shaded area. So make use of your Z. Look for your Z corresponding to 32. So it will be 32.2 by sigma by root n. So it will be minus 1.33. So probability of Z to be greater than minus 1.33, it must be 0.9082. Is it clear?
Yes.
So that's how for mean we make use of the sampling distribution. Similarly, for proportions also we can use. Okay, another example. The deans claim the average weekly income of MBA graduates 1 year after graduation is $600. So this is the mean. Suppose the distribution of weekly income has a standard deviation of $100. What is the probability that 25 randomly selected graduates have an average weekly income of less than $550? Very similar. I want probability of X bar to be less than 550, where X bar follows a normal distribution with mean 600 and standard deviation 100 by root 25. So corresponding to 550, the Z value becomes minus 2.5. So probability of Z to be less than minus 2.5 is 0.0062. Is it clear? Mansur?
Yes.
Saurabh?
Yes. Yes. Clear.
So now we can look for the sampling distribution of sample proportions. Very similarly, what we have got, P cap to follow a normal distribution. It follows a normal distribution with mean equal to P and standard deviation root PQ by N. Root PQ by N. Very clear? So again, using central limit theorem, for sufficiently large values of N, and especially when NP is greater than or equal to 5 and NQ is greater than or equal to 5, then we can go in for the approximation for the binomial distribution to be equal to the normal distributions. Very clear?
So only if it's equal or more than 5.
Yes, if NP and NQ are greater than or equal to 5, we can look for using the normal distribution in case of binomial situation also. So if P cap happens to be sample proportion, let us say x by n, then P cap follows or it approaches the normal distribution with mean equal to P and standard deviation root PQ by n. Sometimes this is also called standard error of the proportion. Just like we say standard error of mean, we call it as standard error of proportion. We can call this as standard error of proportion. Standard error of mean and standard error of proportion. Root PQ by n is called the standard error of proportion. So we know that P cap follows normal distribution with mean P and standard error root PQ by n. So what is the formula for Z? Z will be P cap minus P by root PQ by n. So that follows a standard normal distribution. Are you with me?
Yes.
Exactly similar. The variable that is P cap minus P by root PQ by n. So that is the formula for Z. So Z is given by P cap minus P by the standard error or the standard deviation of the proportion. So that is nothing but root PQ by n. Q is 1 minus P. Is it clear? So this follows a standard normal distribution. So we can make use of the Z table for arriving at the probabilities. Are you with me?
Yes.
Nice. Yes. Okay. So you can look for an example. Okay. So this approximation generally it is valid only when NP and NQ are greater than or equal to 5. So let us look at an example. A state representative received 52% of the votes in the last election. 1 year later, the representative wanted to study his popularity. If his popularity has not changed, what is the probability that more than half the sample of 300 voters would vote for him? First thing you must realize that it is a case of proportions. Whether he will get a vote or he will not get a vote. So only two outcomes are there. So basically it is a binomial situation. Are you with me?
Yes.
Yes.
Okay. So what is given? The representative received 52%. So what is P? P is 0.52. Here, 52%. So he received 52% of the votes. So the proportion who voted for him is 0.52. So after 1 year, he wants to know the probability that more than half of the sample of 300 voters will vote for him. More than half of the voters, half means 0.5. So what is the chances that the proportion of voters who vote for him is more than 0.5 when he considers a sample of 300 voters? Are you clear?
Yes.
So I want to know what are the chances that the sample proportion, that is P cap, is more than 0.5. So what is the probability that P cap is more than 0.5 given that P is 0.52 and N is 300. So if I want to make use of the normal distribution, what are the condition? NP and NQ are greater than or equal to 5, isn't it? So what I have got, N is 300, P is 0.52. What is NP? NP is 300 times 0.52, that is 156. It is more than 5. Similarly, NQ is 144, so it is also greater than 5. So I would make use of the normal distribution. So the assumptions for application is satisfied. So I can make use of the normal distribution. So what is the Z value? Z is given by P cap minus P by root PQ by N. So I calculate P cap minus P by root PQ by N. This is my Z. So what is the probability of Z to be greater than the calculated value? What is the calculated value? P cap is 0.5 minus 0.52 by root of this value. So what is this value? Can you tell me? 0.5 minus 0.52 divided by root of 0.52 into 1 minus 0.52 by 300. How much you will get? Can you calculate and tell me?
Yeah, just calculating, just a second.
Yeah. All of you can calculate and cross check.
0.0. No, just a second. It's 0.7, around 0.7, I think.
I think it must be negative, isn't it? 0.50 minus 0.52. It must be minus 0.52 divided by some value.
Yeah. The value, you mean the, yeah, 0.7.
Numerator is negative
total, I
0.7.
mean.
Yeah,
Yeah,
it is
0.2
negative 0.7.
divided. Yeah.
Yeah, negative 0.02 divided by the root of that value. So it should be a negative value. So you can look for the probability of Z to be greater than minus 0.7. So it will be somewhere close to 0.7549. You can cross check. Is it clear?
Yes.
So that's how you can make use of the, yes.
I just have a question, Doctor.
Yeah,
why do we consider this question as binomial?
Because there are only two outcomes. What is the situation? A state representative received 52% of the votes in the last election. So either he receives a positive vote or a negative vote. He receives a vote or no vote, isn't it?
Yes, yes.
Only two outcomes are there.
Oh, okay, okay.
So you are looking for the proportion. Very clear?
Clear, yes.
So please look at the situation. So you are looking at only two outcomes, two possibilities. Either he gets the vote or he won't get the vote. So 52% votes he received. So proportion of votes he received is 0.52. So this is the case of proportions. So we can approximate it to normal distribution because NP and NQ are greater than or equal to 5. So I am looking at the sampling distribution of P cap, the sample proportion, which is a normal distribution with mean P and standard deviation root PQ by N. So I make use of the formula for Z using the proportions and use the table for standard normal distribution. Is it clear?
Yes.
So that's how we can make use of the applications of sampling distributions of mean and proportions for arriving at the probabilities by making use of the central limit theorem. So this is about this sampling distributions. So this completes our topic on sampling distributions. Then we will go in for the next topic. That will be our confidence intervals, estimation and confidence intervals. So maybe we can take it up in our next class. Will be okay?
Yes, it sounds good.
Yes.
So do you have any questions? Whatever we have done so far?
Yes, Doctor, I have a question.
Please go ahead.
For the last proportion, why we call it standard error instead of standard deviation?
Just to distinguish between the standard deviation for the population and the standard deviation for the mean, that is variable x and x bar, p and p cap. The
Okay.
distinction, that is the name given. Okay. Standard deviation of the mean, we call it as standard error.
Okay.
Okay. So to distinguish clearly between the standard deviation for x and standard deviation of x bar.
Okay, clear.
Yes. Any other questions, please? So please go through this carefully. I will put up a set of discussion questions, and then I will also put up the next topic. We will continue with our learning. Shall we continue with our this online? Is it okay?
Yeah.
Yeah, it's better.
So next week we are meeting again online at the same time. That is at 4 p.m.
Same
Okay.
time.
Same time.
Okay.
Yes,
Okay.
Mr. Saud.
Okay.
Okay, thank you, Doctor.
Regarding discussion 3,
Yeah.
discussion 3 is related to distribution, probability
Yeah,
distribution.
probability distributions, the binomial, Poisson, as well as normal distribution, and a general discrete probability distribution.
So discussion 3, the one you sent, is not related to the sampling distribution.
No. Sampling
Okay.
distribution, it will be discussion 4.
And for the midterm, we have everything except for the sampling distribution and after.
Yeah, so only 1, 2, and 3.
But that doesn't include sampling.
This is
In the
4.
exam.
Sampling distribution is in chapter 4. So this is not
Chapter
there for
4.
your midterm.
Okay.
Okay. So chapters 1, 2, 3, discussions 1, 2, 3.
Okay.
Clear?
Clear. Yes.
Okay.
Thank you.
Yeah. Any other questions, please? Okay, then we'll stop here for today. Yes, we have anything to ask, Mr.
No.
Abdul Majid?
No.
Okay. So have a good time. Make best use of time. We will meet again next week at the same time at 4 p.m. on Sunday. Okay.
Okay. Thank you.
Thank
Doctor.
you.
Thank you.
Thank you.
Take care. Bye.
Thank you, Doctor.
Thank you.